Hey everybody, we're going to go ahead and start off our next video. So this is going to be 8.3 that we're dealing with here. And we're still going to be talking about the strength of acids in solution. We're still going to deal with pH, finding the pH when we need to. But now we're going to go into a little bit more in depth, and we're going to actually spend a lot of time looking at reactions as a whole. Now, you're going to notice that we're dealing a lot with weak acids here as well. So instead of the strong ones, because we know how the strong acids are going to behave, we're going to actually spend a little bit more time focusing on what happens with our weak acids. Our goal is we want to be able to determine the pH of a weak acid from a given reaction. That means we're going to have to look at the Ka values. That means we're going to have to compare a few things, and also means the reintroduction of our good friends, the ice table. So we want to go ahead and get started right in here. Now, when we think about acid-base problems, there are a couple of questions that we have to answer. First, what are the major species in solution? What is the dominant reaction that's taking place? Is it going to be at equilibrium, or is it going to go to completion? Will it react all the major species until you're left with the equilibrium reaction, or what do we have? And last but not least, pH if we need it. Again, what are the major species? What's the dominant reaction? How is it going to play out in terms of equilibrium and pH if the question calls for it? Now, we're going to look at a few examples here and see how we can, I guess, accompany or accommodate all of these questions. So, looking at the following scenario, consider an aqueous solution of 2.0 times 10 to the negative third molar hydrochloric acid. What are the major species in solution? Well, things we need to do is, oops, sorry, wanted to go back. We need to figure out what is our reaction in the first place. Because it's aqueous, that means we're going to be looking at HCl plus H2O. And it's going to form, we're going to have the donation of this hydrogen from our HCl, because we know it's one of our strong. So it's H3O plus Cl minus. Now, when this reaction goes into play, we need to know what are the main things that we're focused on. Well, let's see. We know that water is going to be involved. We know that our hydrogen ions are going to be involved, and we know chlorine. Why do we know that I don't have to worry about HCl? Well, because it's going to dissociate completely. So the major species that we have are hydrogen ion, Cl minus, and water. The question is then asked, what is our pH? Well, let's take a look. How do we find pH from the previous section? We used negative log of the hydrogen ion concentration. And because we know that this is a strong acid, that means that our hydrogen ion concentration is going to be very similar, almost equivalent to this value. So 2.0 times 10 to the negative 3. And we're actually going to plug that in, and we should come out with a value of pH of 2.70, 2.69 approximately. Now, this part was very straightforward. We looked at the concentration we had and the fact that it's fairly small concentration, but this is where we're actually going to start. What about if we have a concentration, the pH of a concentration 1.5 times 10 to the negative 11 molar solution of HCl? Well, in that case, we have to consider a few things. What do you mean? Well, if I'm trying to find this, it's not going to come out to 10.82, which I know is what a lot of you guys are going to go to. Immediately you're thinking, okay, just plug in the concentration and things are fine. But look at the concentration that we're dealing with here. That means if we use this value, that we're going to end up with something basic. And we know that HCl itself is not a basic solution. So we have to look at what the other reaction is that's in play. And the other reaction that we have that's in play, oops, sorry, let me close this out. The other reaction that we have that's in play is also going to be H2O plus H2O yielding H3O plus OH minus. And our concentration, our value that we're going to look at here is going to be equivalent to 1.0 times 10 to the negative 7. So if we take that and plug that into our situation, we're going to end up with a pH of 7. Now, again, pointing out that if you try to pull in this value as it is, we're going to end up with a pH of almost 11. That doesn't work for HCl. We know that it's going to be acidic, so we know that there's a problem. We have to look at both possible reactions that are happening. Now, calculate the pH of 1.5 times 10 to the negative 2 of our nitric acid. Well, again, the question is, what are the major species we have? So if we have this reaction, we have HNO3 plus H2O is going to form H3O plus NO3 minus. Now, major species, just like we dealt with before, we know that this is going to be a strong acid, a very strong acid, so our major species, H2O, H3O plus, or H plus, and NO3 minus. Now, we know that despite this, our reaction at our major donor, of hydrogen ions is actually going to be from our nitric acid. So, HNO3, we know that we have about this concentration of hydrogen ions, so we're going to take the negative log of 1.5 times 10 to the negative 2, which gives us a pH of approximately 1.82. Oops. Now, when we look at this overall picture, and this is actually what's going to lead us in that direction, when we look at this picture, nitric acid added to water, we immediately get this reaction that we just talked about. Now, why is this not very likely to happen? Well, let's think about it. What do we know about nitric acid? It's strong, so that means it will not reform. It's gonna, if it's in water, it's gonna immediately dissociate or dissolve. So we know that this reaction not gonna happen. That being the case, this is actually going to be our dominant reaction. Well, that's good, but we know that we have only a small amount of this that's going to be contributed from the water. So that's why we use the nitric acid concentration to actually find out our pH. And we come out with 1.82. Now, look back at this example if you need to. Rewind a little bit. It's perfectly fine because we'll walk through the exact same steps as we walk through this problem. Now, when we're solving weak acid equilibrium problems, again, just like we did before, we're going to list the major species in solution. We're going to choose the one that's going to produce the most hydrogen ion concentration and write the equation for that. We're going to use the equilibrium constants, the Ka values, to determine which one is going to dominate the reaction. Then we'll write the equilibrium expression. Now, a couple more steps. Again, this is weak acids. List the initial concentrations, define the change, and determine the equilibrium concentrations in terms of X. What does this sound like? Well, steps 5 through 7, really 5 through 8, are actually our ice table. So I told you they will be back. Now, the great thing is when we're dealing with our weak acids, remember we said that less than 5% usually dissociates. So this is actually going to make it easy because we get a chance to assume, like you said, that X, the amount that's going to dissociate, is negligible. And we'll talk about that in the next couple of problems. Now, this is what that part is actually talking about. So let's move. It says consider the following. Consider a 0.80 molar aqueous solution of weak acid HCN. What's the major species in solution? Well, let's look at the reaction. If I have HCN plus H2O, I'm going to end up with H3O plus CN minus. Now, in terms of what's happening here, A weak acid, I know it's not going to dissociate much. So the question then becomes, what am I actually getting out of this? And we find that it's actually going to be just the HCN and the water. Why? Because very small amount. If we look at the Ka value, the acid dissociation constant, it's times 10 to the negative 10, so it's all extremely small. So that means there's not much going to happen on this side. It's still there, and we're still going to have to account for it. But the major species in this reaction is going to be our cyanic acid and water. Now, this is what actually is going in. Why aren't H plus and CN? Because again, we're only going to produce a very little. So we got to consider this. Which one is actually going to control the pH? Is it going to be the HCN plus water, or is it going to be water itself? Let's consider the Ka values. Well, Ka for this, 6.2 times 10 to the negative 10, versus the Kw value for water, which is 1 times 10 to the negative 14. Taking a look at this, we know that this value is higher, so it's most likely going to be the one that actually controls this reaction and controls the pH. It's going to determine how much of our hydrogen is actually going to dissociate. Now, we can use that information along down the line to actually figure out the pH, but that's where we're moving to next. Now, we're going to go to a completely different reaction, but we're still going to use that same concept a little bit further. Now, calculate the pH of a 0.5 molar aqueous solution of hydrofluoric acid. Again, it's a weak acid that we're going to be dealing with. Now, what are the major species? Well, let's take a look. I have HF plus H2O is going to yield H plus F minus. Major species, hydrofluoric acid and water. Our equilibrium lies far to the left. So we need to know which reaction, oops, sorry, we just did this part. Why aren't H plus and F minus? Because the equilibrium lies so far to the left, we don't produce much of them. Now, which of our reaction is going to be dominant? Let's look at the values that we have. We have hydrofluoric acid with a Ka value of 7.2 times 10 to the negative 4, and we have the water dissociation constant of 1.0 times 10 to the negative 14, which has the higher value. Of course, the top one. So this is the one that's going to control our pH. So now we plug it into our good old friend, the ice table. We know we started off with 0.5 molar solution here and approximately 0 here. The change is going to go from the 0.5 that we have to the other side. It's going to shift towards the right. So we just need to determine how much. Well, if I have x squared, x times x, over 0.5 with a Ka value here, we can move to determine what the hydrogen ion concentration is actually going to be. So if we plug this in, I'll write it here. X squared over 0.5 minus x equals this value, 7.2. Let's erase this part and make it a little bit clear that it's 7. 7.2 times 10 to the negative 4. I can assume, because it's a weak acid, that it's going to be negligible, so I'm going to cross that out. I'm going to end up solving for x. So 0.5 times this value is going to give me 3.6 times 10 to the negative 4 equals x squared. Take the square root of both sides, and I should end up with, 0.0189, it looks like, equals x, and I can use that to determine my pH by just taking the negative log. So pH 1.72. Now check my work to make sure I haven't done anything wrong or gone crazy here, because I want to make sure that you understand what's going on. Now, what we can do also to check and make sure that this works is we find what's called the percent dissociation. What we do is we look at the amount dissociated based on our previous step here. So we're saying that we only lost 0.018 189 in terms of our concentration. What we're going to do is we're going to divide that by the initial concentration, what we started with, and multiply by 100. If we get a value less than 5%, we know that we were okay as far as skipping out on that on the minus x part. If we get anything over that, then we may have to go back and reevaluate. Now, let's look at another example. Sorry. It says a solution of 8 molar formic acid is 0.47% ionized in water. Calculate the Ka value for formic acid. Well, let's take a look at the information that's given to us. It already tells us that we have an 8 molar solution, and it already tells us that it's 0.47% dissociated. So one thing that I'm going to do that make things a little bit easier is I'm going to go ahead and multiply my 8.00 molar times 0.0047. This is our percentage turned into a decimal. Now, when I do this, I'm going to come out with 0.038 approximately. This lets me know actually what my calculations are going to be. What do I mean? Well, let's look at the reaction. CHO2 plus H2O yields H plus CHO2. Well, according to the reaction, water we know is going to be the same, but I started off at 8 molar, 0 and 0. My change is going to be minus x here. Oops, sorry, not minus x, because I actually know what the value is going to be. The value that I actually have is 0.038. That means that this is going to be plus 0.038 plus 0.038. Now, that means my equilibrium, 8.0 minus 0.038, 0.038, 0.038, and I can plug that in to actually get my Ka value. 0.038 squared all the way over, what is it, 7.62. 7.962, sorry. Plug that in, 962, and this will give me my Ka value. Now, if I can go ahead and clear the ink from the screen, you can go ahead and see in your calculator what value you got there. And we should come out with 1.8 times 10 to the negative 4. Now, you're going to need this information as we continue on, so please make sure you sort of highlight and write it down. Now, if we have a solution with this value and it asks us to calculate the pH of that solution, we're going to use the same information that we had before. Well, before we figured out that we had about 0.038 molar hydrogen ion concentration. So, if I need the pH of that, I'm going to do negative log of my 0.038, which should give me a value, pH of approximately 1.42. So these problems can be asked many different ways, and it sort of builds on each other. So as you're preparing for the AP exam and the FRQs that you're going to get, remember that you're going to need piece by piece. It's all going to work together. Now, if we compare a couple of things here, we want to have an idea of how we can compare. What do I mean? The value of Ka for 4.0 molar formic acid should be blank, higher than, lower than, or the same as the Ka for 8.0. This is sort of a trick question. What do I mean? Well, Ka is the acid dissociation constant. It has nothing to do with the initial concentration. So that being the case, that means it should be the same as. It should be the same as. Now, what about the percent ionization of 4.0 molar versus 8.0 molar? Well, if that's the case, that means that, sorry, let me take this, HCHO2 plus H2O, it's going to be H plus CHO2 minus. Now, for me to go from 8 molar to 4 molar, that means I'm going to have to add water. Well, if that's the case, if I'm adding water here, according to what we already understand about equilibrium, what's going to happen to the overall reaction? Well, if I add water, that's going to shift it in this direction. That means I'm going to have more of this that ionizes. I'm going to have a higher percent ionization. Now, what's that going to do to the concentration? If I dilute it, and even though I have a higher percentage ionization, my hydrogen ion concentration is also going to be lower. So if my hydrogen ion concentration is lower, that means that I'm also going to end up with a higher pH value, meaning more towards neutral, more towards the basic side of things. Change the concentration, I change my pH value. Now, here's our next example. It says calculate the percent ionization of 4.0 molar formic acid in water. So we need to discover a few things. We need to look at what the actual, what are the major species and how it's all going to work together. So, sorry, the answer is already there, but we're still going to work through and see how we can check it. So let's take a look at it. Well, what's our reaction? We have HCHO2 plus H2O is going to yield H plus CHO2 minus. Now, we know that our major species, because it's a weak acid, are going to lie on the left. So our major species, HCHO2 and H2O. Which one is going to be the dominant reaction? Well, is it going to be the formic acid or is it going to be the water? H2O plus H2O yielding H3O plus OH minus. Well, let's look at the values that we have. We already have the acid dissociation constant for our formic acid, and we compare it to the 1.0 times 10 to the negative 14 for our water. We know that this is going to be our dominant reaction. So let's go ahead and run with that now. So my reaction, CHO2 plus H2O yields H plus CHO2 minus. Well, if we know we're starting off with 4.0 molar, we know that water is the same as constant, 0, 0. We know that the reaction is going to shift in that direction. So minus X plus X plus X. Equilibrium is going to be 4 minus X, X, X. Let's go ahead and plug in our values to find out what we're going to get here. So if I have 1.8 times 10 to the negative 4 equals X squared over 4 minus X. Again, we're going to assume that I don't have to worry about the minus X because it's negligible. It should be less than 5%. Multiply both sides by 4. Once I do, I'm going to end up with approximately 7.2 times 10 to the negative 4. 7.2 negative 4 equals X squared. Square root of both sides. I'm going to get 0.268 or 0.27. I'll go ahead and do it that way. 0.27 equals X. Now, to figure out the percent ionization, I'm just going to put this concentration divided by our initial, which is 4, and see what we come out to. So 0.27 divided by 4 times 100. And I'm going to get 0.67%, which is what we saw on the slide just a little bit before this. Now, I realize that this video is a little bit longer than usual. And I ask that you continue to bear with me on these because we're doing a lot of examples. I want to make sure you understand what's happening. One last problem that we'll do, and then we'll call it a quit for this video. We want to calculate the pH of a 4.0 molar formic acid. Well, we can use the information that we gathered in the last slide and actually proceed with that. What do I mean? Well, on the last slide, we found that the concentration of hydrogen ions was 0.27 molar. So, oh, sorry, 0.027 molar. Almost made that mistake. So, I'm just going to do negative log of my molarity, 0.027, which gives me a pH of approximately 1.57. Now, my hope is that you're starting to pick up on how this all sort of works. Again, what's the reaction? What are the dominant species? Sorry, what's the dominant reaction? And based on that, we can proceed to do the rest. Now, this is where we're going to end this one, and I want you to take some time, look over the examples, rewind a couple times, and just look at the practice that we're going to be working on in class. I want to make sure that you understand and that you feel comfortable with it so that you can proceed with it on the take-home test. Have a good evening, and look forward to seeing you in class.